Hello, everyone. Can you see us? Can you hear us?
Yeah, I can hear you just fine.
Can everyone else hear us and see us?
Yeah, getting some messages.
Super. Okay. Hello, everyone, and welcome to today's white paper presentation, The Path of Intelligent Engine Diagnostics. We'd like to thank you for taking the time and joining us today. My name is Mila, and I work on the marketing team here at Datum, and I'm excited to be hosting this session today. And I'm pleased to introduce today's speaker, Konstantinos Titilonis, who is going to explain how a single continuous measurement of instantaneous crankshaft torque can measure engine degradation and efficiency in real time, avoid its imminent failures, and improve a vessel's energy efficiency. And before I hand the mic over to Konstantinos, I'd like to let you know that we'll be running a live Q&A session at the end of the presentation. So if you have any questions, just pop them in the chat section on the right of your screens and we'll answer them then. And without further ado, I'd like to kick things off by welcoming our presenter, Kostas. Over to you.
Thank you very much, Mila. Let me start the presentation. All right. So, the path to intelligent engine diagnostics. So as Mila already said, we're going to talk about how from the measurement of torque, we end up getting very, very useful information about our engine, about the in-cylinder pressure and the progress that we've made so far in deciphering all this huge puzzle that we end up deploying in our recently launched product called Datum Hawk. So we're going to give you the details about how all of that connects. And essentially, in this presentation, what we want to underpin is that we use a continuous foundation of research in order to funnel that into Datum Hawk and have a direct contact with the client that allows us both to improve and also add value to the ship owner's business. So let's begin. First of all, a few words about myself. I started the research on energy management projects of offshore oil rigs in the Kim Kraft's shipyard in Yantai. And this was my first contact with the area of research and energy management. Subsequently, I worked in the Strathclyde University's Maritime Safety Research Center, MSRC, and developed a novel methodology on energy management of ships' propulsion engines, which in a sense might be slightly similar to what we do right here. It has definitely got a lot to do with engine modeling. And lastly, I'm working here in R&D through a joint partnership with Strathclyde University on intelligent diagnostic techniques. And this is also what provides huge foundation to this project, is that we're being backed by the University of Strathclyde and their knowledge, which is built over decades in engine modeling and maintenance techniques. Right, so a very general overview. How do we perform engine diagnostics for the most part? First of all, this burden falls on the shoulders of the ship owner. And the ship owner has a lot on their plate. They have to do with their technical management of their fleet. They have to do with legal aspects and compliance. They have to do with the financial aspects, especially in a market that seems to be so volatile. So naturally, there's not a lot of time left in their hands. So a ship owner would use three basic things in terms of engine diagnostics. First is assessment by experience. So you have an experienced engineer on board, he walks around the engine, he sees things, he hears things, and reports accordingly. Second of all, we have one-off inspections. So we have pressure measurements, oil sampling, vibration measurements. These may be done usually once a year. We have clients that do some of these once per 4 months, but unfortunately they are by no means continuous measurements, and they can miss the onset of faults, which may end up being very costly to the ship owner. And last, we have another technique which involves basic spreadsheets. So whatever data is being collected, either by hand or by whatever the system, existing monitoring system that is on board, is being processed by someone at the office. And essentially, as you can see in that small little picture there, it tends to be quite chaotic. So this is, for example, a power versus RPM graph. And just by looking at the spread of the data and how massive it is, it becomes very quickly apparent that advanced techniques are required. And this cannot just simply be a side project for an assistant superintendent that's being assigned to draw some propeller curves. So that's an extremely challenging data set to implement. So therefore, all of these measurements have their own respective advantages as well as drawbacks. And what we're looking to see here is how we can make a contribution here in Datum Electronics, such that we can lessen and improve the burden that the ship owner is having on their shoulders, so that they don't have to, so they have to automate their decision-making procedures in terms of maintenance and diagnostics, as well as not having to worry about these things directly themselves, and by bringing state-of-the-art technologies, as we're about to explain. So, as I already started to explain, what's the need to innovate? Well, we want to first of all help implement the state-of-the-art of monitoring and diagnostics technology. And with the onset of digitalization these days, it's almost a requisite that everybody should be involved with these kind of things, because there are massive benefits to gain. Also, we are facing extremely volatile global markets with global fuel markets uncertainty, as well as massively fluctuating profit margins, which is actually not only a recent problem, but it tends to be recurrent, especially in the shipping industry. We tend to have a lot of booms and busts. In addition, we are facing quite large costs, as well. The increasing machinery complexity increases the maintenance costs, and also there is costly downtime. As a matter of fact, I remember seeing a report from the Swedish P&I Club, which claims that the claims for machinery breakdown are steadily increasing over the last decade. The last, and it's also a very important topic, we have to deal with compliance. So IMO has a new regulatory agenda with things such as the EEDX, which might be implemented. We have the EU Green Deal and the UK Clean Maritime Plan, and all of these will be things that will push the ship owner to run very, very efficient engines, and also, respectively, might reduce the profit margins. So cost savings are even more essential. So this is just a summary of what we just talked about, and essentially this is what gives us the need to innovate and introduce this new technology in the industry. So Datum Hawk. Why is it the future of condition monitoring? First, let's explain what this system actually does. As we hinted at the beginning of the presentation, our emphasis here has to do with torque. And that's because here at Datum Electronics, we've studied the measurement of torque for years and decades in the past, and we've managed to perfect that. As you can see here, we have our torque meter product, which is included as a standard part of the Datum Hawk monitoring system. So essentially, currently, the Datum Hawk system is an advanced condition monitoring system. And it includes sensors such as torque, flow meter, and it can be integrated with any other sensor on board as the requirements are according to our client. For example, we have a client now that's looking to integrate the system with the engine's CAN bus, so we can obtain other data as well. This is extremely useful for us, such as scavenger pressures, temperatures, etc. But most importantly, Datum Hawk is a platform that is continuously developing and uses intelligent engine diagnostics algorithms. So we obtain data, we process them, we develop algorithms to explain the phenomena that we see and that can improve the operation of the engine, and we feed it back into the system. So that's the idea behind it. So how does it work? In order to address this, we have to address it through a three-step process. First, we have to understand what the vital measurements are, which we're looking to collect. And in these vital measurements, of course, is the instantaneous crankshaft torque, or otherwise the engine's torque profile. Then we have to discuss about how we can understand this measurement and how we can interpret the data provided by this measurement. And thirdly, we have to see how from this interpretation we can actually obtain useful information about our engine. It's going to help us. So, the vital measurements. So, as we said in the beginning, engine monitoring can be done in many ways. And primarily, we measure engine temperatures, fuel consumption, we do oil sampling, we measure the in-cylinder pressures. However, we have to keep in mind, when we're measuring something, it has to fulfill 4 criteria. The first one is, whatever is being measured has to be measured accurately. So we have to have a high confidence that the value that we're actually recording is an accurate one. Secondly, it has to be measured cheaply. For example, it would be great if we had an airflow sensor in the engine after the engine's turbocharger, so we can see what the mass airflow is, but this would be absurdly expensive. Thirdly, this measurement has to be performed continuously. So this is a very important point that we're stressing throughout this presentation, is that for these techniques to be effective, there needs to be continuous monitoring so that we can actually detect the onset of faults and be able to diagnose beforehand, before they actually blow out of proportion and increase the cost of operation with costly downtime, etc., etc. And last, these measurements should be able to provide useful information about the engine. Certainly, the more we can measure, the better, but we have to sort of narrow it down to key measurements. For example, the scavenger pressure is an extremely useful measurement, but it certainly doesn't tell us as much as the in-cylinder pressure. So there's certainly a way to categorize things. And obviously, as systems expand, more measurements are beneficial. But in this industry where we're looking to minimize our costs, we're trying to attack things from a top-down approach by looking at first the most important measurements, and then all the other measurements that explain the secondary effects. So let's start with the in-cylinder pressure. So it's undoubtedly the most useful, amongst the most useful measurements that we can get, that tells us what is actually going on within the cylinder. So as you can see here on the right-hand side, you can easily see how a healthy condition is different from a condition where we have a fouled injector, or where we have some detuned or differently tuned timing with advanced injection timing, which the engine might sometimes get detuned if it logs in more operational hours. So we have a lot of experience, and not just us in Datum Hawk, but also the ship owner, in interpreting in-cylinder pressure diagrams. That's why it's so important. So it can reveal, as we said, differences such as differences in fuel quality, injector condition, engine tuning and degradation, as well as blow-by. So these are very important things that we can know about our engine. However, it's very hard to perform continuous in-cylinder pressure measurements, not only because we have to deploy a network of sensors to all cylinders that have to be synchronized, but because it's a very expensive thing to do. Right, so this is where the instantaneous crankshaft torque comes in. So for example, we see here what we call a torque profile of a V12 engine. So along 720 degrees in the crankshaft. So we see lots of ups and downs, and this is actually how the torque fluctuates instantaneously within the engine. And that gives us the first hint that whatever is happening within the cylinder, it actually gets translated into the engine's torque. However, as we can see here, the effects may be fairly complicated, so we cannot tell just by looking at this whether the engine is healthy or not. But certainly, one of the very important things of the instantaneous crankshaft torque is that it can be obtained accurately, extremely accurately in our case, and be continuously monitored. And also, one sensor obtains information about all the cylinders, but by measuring the engine's torque profile. So let's see how we can understand the crankshaft dynamics so we can actually be able to establish a relationship between the in-cylinder pressure and the torque that we're actually measuring. So the way to do this is to develop a crankshaft dynamics model. So to interpret the information in the instantaneous crankshaft torque, as we said, its relationship with the in-cylinder pressure should be determined. And for that, we need to examine the engine torque and how it's being transferred to the engine's load. So there are a few mechanisms that this is happening. First of all, we have combustion torque from the combustion gases within each cylinder. Then we have torque that's opposing the combustion torque, which includes the friction torque on the liner, on the cylinder liner, as well as all the main bearings. Then, and most importantly, which is something that's not intuitive, we have the crankshaft structural damping as well as flexibility torque. So we have a lot of absorption from the structural flexibility and the structural damping as well as the crankshaft flexibility. So as it flexes within all of these loads exerted on it, it actually translates the torque signal. And last, we have the engine load torque, which is what our propeller would absorb, or the generator. So if we put all of these together and create a crankshaft dynamics model, this is what we've actually done over the past year. So we've put together a crankshaft dynamics model that takes very basic inputs. For example, the in-cylinder pressure for every cylinder, the basic information regarding the engine, for example, number of cylinders, the stroke, as well as torsional vibration analysis coefficients. So the torsional vibration analysis is a piece of paper that we pretty much get after the installation of the engine when it's brand new on the vessel, and it's certified that there are no hazardous vibrations. And the information contained within there is used in the crankshaft dynamics model. So this comes with all engines. And with that, we're able to model and predict what the engine's torque profile will be. So how is this actually useful? Well, first of all, we have to validate the model. And actually, that's what we've done. So the model was successfully tested in the case of a 10-cylinder, 2-stroke diesel engine. So as we can see here in the continuous line, the black line, the instantaneous torque within 360 degrees is actually fluctuating quite a bit. It has an average value, which is what the engine's torque would be in what we call steady state, but instantaneously it's actually varying by quite a bit. And we were actually surprised to see that, but the model confirmed it, that this is true. This is actually what is happening instantaneously. And another interesting fact is that the engine has 10 cylinders in this specific case, and we are able to observe 1, 2, 3, 4, 5 distinct peaks in the engine's torque profile. So that tells us right there that there is a relationship, between those two. So having modeled that and being able to predict the engine's instantaneous crankshaft torque, we can now start obtaining critical information and see how we can perform diagnostics. So the first thing we can do is start doing what we call failure mapping. So if we have the crankshaft dynamics model and we are able to predict the torque, then we can simulate faults. So for example, we know pretty well, as we said before, how a faulty in-cylinder pressure diagram looks like. So we can virtually introduce a fault on cylinder 1 and then see how the engine instantaneous crankshaft torque reacts. then we can virtually introduce another fault and then another, and we can do this thousands of times, as many as we like, so that we can obtain a map of many conditions that are faulty and their corresponding instantaneous crankshaft torque or engine profile. And we can see this in this figure. So the green would be the green signal that goes up and down would be the healthy engine. Then we've got the red signal, which would be the fouled injector at cylinder number 2, which is a fault that we have actually simulated. And we can see that there is actually a very subtle difference between these two signals, but certainly measurable difference. And then, just to show the other extreme, we've introduced a complete misfire at cylinder number 5, which is the yellow line that we can see is drastically different from the baseline signal. So the idea here is that we have a baseline signal, we know how our engine behaves in healthy conditions, we have data for that, and we're able to simulate any other faulty condition. Consequently, when we measure something that's out of the ordinary, we can match it to any other condition that we've produced a fault for. So this is the first technique. Now, that's quite an important part, and that is actually a breakthrough that we've had in the last month of continual development in the Datum Hawk system. Since we are able to go one way, and with certain inputs in the model, we're able to predict what the engine's torque profile will be, and hence try to correlate if there is any fault, we can certainly go the other way. So we've actually developed a model that seems to be successfully working under the conditions that we've tested it, that using the measured torque profile, it can actually reproduce the in-cylinder pressure. So actually, that's what we see here, and that's a real test. We see the engine torque profile on the left-hand side. It goes through the inverse crankshaft dynamics model, and we actually managed to get the pressures with a really good match to the measured. So as you can see, they're slightly different. Cylinder 2 appears to have a slightly higher pressure, as well as cylinder 5. And cylinder 1 appears to have a fairly low pressure. It seems to be the lowest out of all. The differences are quite small, but this is what's being expected. So right away, what looks odd in this one is cylinders 2, 5, and 9. We can see the pressures that are slightly higher for some reason. And certainly cylinder 1 looks fairly low. So on top of that, if we were to compare this with the shop tests of the engine, where we have the brand new condition of how the in-cylinder pressure should look like, we can see which cylinders are way off, and hence what we can do about those. So certainly this gives us a very good tool in order to be able to instantaneously, under all conditions, predict the in-cylinder pressure for all cylinders using just the instantaneous crankshaft torque. So, what's the conclusion? So we have a lot of future plans laid out, especially after this recent breakthrough. The first one is that we're looking to integrate the crankshaft dynamics model and the inverse model that we just saw with an already developed thermodynamics model, as you can see here. So this thermodynamic model takes things a bit further. So we don't just see the pressure curve and make assumptions and conclusions based on that. It actually pinpoints component-wise what the degradations are. So this is what the usefulness of the thermodynamics model is. Certainly, it might require a bit more measurements like scavenger pressures and certain temperatures, but these are certainly obtainable if we have a system such as Datum Hawk. In addition, we can run a frequency analysis on the engine torque profile to determine failures which do not impact greatly the in-cylinder pressure and might not be necessarily identifiable very, very easily with the inverse model. So as we can see here, we've run a couple of tests by performing frequency analysis on the instantaneous crankshaft torque signal by coupling the thermodynamics model and the crankshaft dynamics model in order to simulate as accurately as we possibly can faults. And we've actually determined that a leaking exhaust gas valve in the specific engine that we are studying, the 10-cylinder two-stroke engine, has a distinct and a unique signature in the frequency domain. So if we were to perform this technique, we'd be able, in this engine, we'd be able to see whether the exhaust gas valve is leaking. So in a nutshell, we're looking to improve the self-adaptive algorithm employed in the inverse dynamics model in order to be able to address as many engines as it possibly can, smaller, larger two-stroke engines, as well as four-stroke engines. Each one of those, of course, has different dynamics, but obviously that's what we're looking to do, improve the robustness so we can capture all of this. And then we're looking to couple a crankshaft dynamics model with a thermodynamics model in order to provide component-wise degradation trends and see component-wise what's going on and inform the ship owner with that. And last, we're looking to integrate the frequency analysis on the instantaneous crankshaft torque signal. So this is it in regards to what Datum Hawk is, how we use the instantaneous crankshaft torque, and pretty much what's the thinking behind it. So I'm certainly looking forward to answering any of the questions that you might have. Right, let's see here.
Thank you, Kostas. Just as a reminder, please be sure to type your questions in the question box on the right of your screen, and we'll answer them now. So I can see questions coming in. There is a question from Tommy. What is the most common failure mode for an engine?
The most common failure mode? For the experience that we have, we're usually looking at slight detuning as they log operational hours. So there's a slight detuning, slight retardation, or slight advance in the injection timing. And as things, progress, we might be able to see, which we haven't seen ourselves, but we've simulated it successfully, differences in quality in the fuel. So this is quite pressing. This is quite a pressing issue, especially as we have the introduction of all of these new blends that we don't know what they do in the engine. So we've certainly seen that in a simulated condition, and in real condition, we've seen changes in tuning.
Okay, thank you. We have a question from Alec. Is there a white paper which we can send to customers in brief?
Yeah, certainly. Let me share the white paper.
We have the white paper attached, and now Kostas will share it so everyone who hasn't read it yet can download it and read it.
There you go. Yeah, just sharing. You can download the white paper. This pretty much explains in a nutshell, again, what has been reiterated in this presentation about how the crankshaft dynamic model works and what's the thinking behind it, how we plan to help the ship owners with that.
Super. We have another question, and it's from Nikolaus. What is the frequency by which the torque meter measurements are taken?
Yeah, this could be configurable. We're looking at anything up to from 800 to 2000 samples per second.
And we also have the question again from Nikolaus. Is this method possible to use with other torque meter makes?
It's not advised to use this method for estimating the in-cylinder pressures with another torque meter. The reason being that this method has been developed using our torque meter with the accuracies that we have and the sample rates that we are obtaining. Therefore, we can't guarantee the success of the results using other torque meters.
Okay, I hope that answers that question. And we have questions from Demetrius. You need in-cylinder measurements. When is the model created? Shop test? Initial period of operation? And how long does it take to gather adequate amount of data to prepare the model? Yeah,
it takes about, I would estimate, about 2 to 3 weeks, just to get enough data, as well as be in contact with the ship owner to arrange to have all those files and manuals transferred over in order to start setting up the model and actually obtain some data that we can start to use and to be able to get some information like you saw.
Okay, does it answer your question, Dimitrios? These are all questions I can see, so if you haven't asked your question and you have one, please feel free to type them.
Yeah, certainly, even after the end of the presentation, you can contact me in LinkedIn, or you can contact us in LinkedIn, and you can answer any of the questions that you might have.
Okay, so we have a bunch more questions. Again, a question from Dimitrios. Each engine has to be modeled separately?
There is a framework of modeling the engine. The model is one, but it requires different inputs. So especially two-stroke engines, they require different inputs, different torsional vibration analysis coefficients, different bore, different stroke. So essentially, the engine is not being remodeled. A different engine is not being remodeled. It's a generic type. A two-stroke engine is a two-stroke engine. So we change certain inputs. So that's what we actually do.
Thank you. And we have a question from Alok. Is there any training from Datum how to monitor the engine?
That is actually something that we're thinking about. We could certainly offer training. However, I'll have to come back to you in order to confirm.
Yeah, Alec, we'll get back to you on that one, if it's okay with you. And we have another question from Nicholas. How many in-cylinder measurements you need to take, and how many loads of the engine?
Ideally, that's the beauty of having a thermodynamics model, is you don't need to take measurements from 0 to 100. You can predict those. You only need to observe the engine operating at some instances to calibrate the model, and then you know pretty much whatever the engine is going to do. So, as I mentioned in our future plans, that's one of the reasons why we're looking to integrate with a thermodynamics model. So we're not having to run the engine from 0 to 100. In reality, with this situation, what we're having is that we can have the in-cylinder pressure, or we can predict the in-cylinder pressure at any point. And usually the engine most frequently operates at only 2 or 3 points. And that's also according to the previous research that I've identified. 2 or 3 points is where most larger two-stroke engines operate most frequently in. So these would certainly suffice, and we can definitely take only these few points, and based on those, tune and calibrate the current models that we have. But in the future, once we integrate the thermodynamics model, it shouldn't be any problem simulating the whole operational range, even at points that we're not going to need. But most likely the engine is going to operate in 2 or 3 most frequently occurring points, about 90% of the time.
Thank you. And we have another question from Nicholas. How's the actual result affected by actual load fluctuations of the engine at sea?
That is essentially what is being captured. Whatever the load is being felt by the propeller is what is being measured, and hence what's being captured by our torque meter. So what you mean by that, if I understand correctly, is that we are able, in the crankshaft dynamics model, to model the propeller, because this is a dynamic load. Actually, there are certain guidelines from the classification societies on how we can include the propeller in not in a crankshaft dynamics model, but how we think of a propeller as a physical object in the ship. So we certainly take into account the propeller and how it absorbs the engine's load. The simplest idea would be the propeller law. On top of that, there are some other things as well, but this is how we model that. How we're capture.
Brilliant. Thank you, Kostas. And we have another question from Demetrius. Are diagnostic results produced automatically or need to be processed onshore by some expert?
At this point, they need to be processed. But as the system evolves, the goal is that this thing is happening automatically. So in 1 year time, in 2 years time, we'll be looking at a fully, automatic system. We've just recently launched Datum Hawk, as I said before, as a monitoring system. But our ambition is that it becomes an automated decision support system. So that's what we're striving to achieve, and that's why we're funneling so much research and investment behind it. So this is being done automatically. But certainly we have to start somewhere, and that's where we're starting at this point, which is we are processing the data so far. We have control over it. We have control over the algorithms. We see what's going on. We see how we generalize them, which is what we are starting to do right now, getting a sense of how to generalize this, not for only one engine, but for everybody's engine. And, we get back the results and we send them back to you as a report.
So what you're saying, Kostas, is the more data the system has, the more autonomous it becomes.
In a sense, yes. In a sense, yeah.
Okay, and we have another question from Demetrius. Are all faults you have identified from simulations, or have results from actual operation?
The actual operation was that last bit, that we were able to identify the pressures and match them. So it wasn't a very, very large envelope. This specific engine, because this specific engine was actually a diesel generator. So it's quite a rare thing to find. But yeah, so this is the experience that we had in terms of actual operation. Currently, the system is about to be deployed in smaller 4-stroke diesel engines. And we'll see also from there. We'll also gain knowledge from there.
Okay, it looks like we've covered all the questions we have. Thank you, everyone. Or maybe not. We have another question. How many ships have you tested your model?
Thus far, the system of Datum Hawk has been deployed in multiple ships. When it comes to these advanced algorithms, which are still in an experimental stage, but they are certainly out there to be tested, we've deployed them as well in a certain amount of ships, which are currently under confidentiality agreement. So if you require anything more specific, especially in regards to your ship, you can come in contact with us.
Great. I guess this is all the questions we have for now, and we would like to thank you everyone for being here, and we appreciate it. And don't forget to download Whitepaper if you haven't already, and if you have any other questions, feel free to contact us on info@datumhawk.com. Thanks again for joining us today, and we'll see you next time.
Thank you, everyone.